Learning objectives. In this chapter, the user will learn the following in detail: viewing pipeline, viewing coordinates, parallel and perspective projections, view volumes and projection transformations, clipping. Clipping. An algorithm for three-dimensional clipping identifies and saves all surface segments within the view volume for display on the output device. All parts of objects that are outside the view volume are discarded. Clipping in 3 dimensions can be accomplished using extensions of 2-dimensional clipping methods. Instead of clipping against straight line window boundaries, we now clip objects against the boundary planes of the view volume. To clip a line segment against the view volume, we would need to test the relative position of the line using the view volume's boundary plane equations. By substituting the line endpoint coordinates into the plane equation of each boundary in turn, we could determine whether the endpoint is inside or outside that boundary. An endpoint x, y, z of a line segment is outside a boundary plane if ax plus by plus cz plus d is greater than 0, where a, b, c and d are the plane parameters for that boundary. Similarly, the point is inside the boundary if ax plus by plus cz plus d is less than 0. Lines with both endpoints outside the boundary plane are discarded, and those with both endpoints inside all boundary planes are saved. The intersection of a line with a boundary is found using the line equations along with the plane equation. Intersection coordinates xi, yi, zi are values that are on the line and that satisfy the plane equation axi plus byi plus czi plus d equals 0. To clip a polygon surface, we can clip the individual polygon edges. First, we could test the coordinate extents against each boundary of the view volume to determine whether the object is completely inside or completely outside that boundary. If the coordinate extents of the objects are inside all boundaries, we save it. If the coordinate extents are outside all boundaries, we discard it. Otherwise, we need to apply the intersection calculations. We could do this by determining the polygon edge intersection positions with the boundary planes of the view volume. As in 2-dimensional viewing, the projection operations can take place before the view volume clipping or after clipping. All objects within the view volume map to the interior of the specified projection window. The last step is to transform the window contents to a 2-dimensional viewport which specifies the location of the display on the output device. Clipping in 2 dimensions is generally performed against an upright rectangle. That is, the clip window is aligned with the x and y axes. This greatly simplifies the clipping calculations because each window boundary is defined by one coordinate value. For example, the intersections of all lines crossing the left boundary of the window have an x-coordinate equal to the left boundary. View volume clipping boundaries are planes whose orientations depend on the type of projection, the projection window, and the position of the projection reference point. Since the front and back clipping planes are parallel to the view plane, each has a constant z-coordinate value. The z-coordinate of the intersections of lines with these planes is simply the z-coordinate of the corresponding plane. But the 4 sides of the view volume can have arbitrary spatial orientations. To find the intersection of a line with one of the view volume boundaries means that we must obtain the equation for the plane containing that boundary polygon. This process is simplified if we convert the view volume before clipping to a rectangular parallelepiped. In other words, we first perform the projection transformation, which converts coordinate values in the view volume to orthographic parallel coordinates. Then we carry out the clipping calculations. Clipping against a regular parallelepiped is much simpler because each surface is now perpendicular to one of the coordinate axes. As seen in this figure, the top and bottom of the view volume are now planes of constant y, the sides are planes of constant x, and the front and back are planes of constant z. The figure shows an object intersecting a rectangular parallelepiped view volume. A line cutting through the top plane of the parallelepiped, for example, has an intersection point whose y-coordinate value is that of the top plane. In the case of an orthographic parallel projection, the view volume is already in a rectangular parallelepiped. Oblique projection view volumes are converted to a rectangular parallelepiped by the shearing operation, and perspective view volumes are converted in general with the combination shear scale transformation. Normalized view volumes. This figure shows the expanded fix transformation pipeline. At the first step, a scene is constructed by transforming object descriptions from modeling coordinates to world coordinates. Next, a view mapping converts the world descriptions to viewing coordinates. At the projection stage, the viewing coordinates are transformed to projection coordinates, which effectively converts a view volume into a rectangular parallelepiped. Then the parallelepiped is mapped onto the unit cube, a normalized view volume called the normalized projection coordinate system. The mapping to normalized projection coordinates is accomplished by transforming points within the rectangular parallelepiped into position within a specified three-dimensional viewport which occupies part or all of the unit cube. Finally, at the workstation stage, normalized projection coordinates are converted to device coordinates for display. The normalized view volume is a region defined by the planes x equals 0, x equals 1, y equals 0, y equals 1, z equals 0, and z equals 1. A similar transformation sequence is used in other graphics packages with individual variations depending on the system. The GL package, for example, maps the rectangular parallelepiped into the interior of a cube with boundary planes at positions plus or minus 1 in each coordinate direction. There are several advantages to clipping against the unit cube instead of the original view, volume, or even the rectangular parallelepiped in projection coordinates. First, the normalized view volume provides a standard shape for representing any sized view volume. This separates the viewing transformations from any workstation considerations, and the unit cube then can be mapped to a workstation of any size. Second, clipping procedures are simplified and standardized with unit clipping planes or the viewport planes, and additional clipping planes can be specified within the normalized space before transforming to device coordinates. Third, depth queuing and visible surface determination are simplified since the z-axis always points towards a viewer. The projection reference point has now been transformed to the z-axis. Front faces of objects are those with normal vectors having a component along the positive z direction, and back surfaces are facing in the negative z direction. Mapping positions within the rectangular view volume to a three-dimensional rectangular viewport is accomplished with a combination of scaling and translation similar to the operations needed for a two-dimensional window to viewport mapping. The three-dimensional transformation matrix for these operations is in the form shown below. Factors dx, dy, and dz are the ratios of the dimensions of the viewport are given here. Regular parallelepiped view volume in the x, y, and z direction is shown in the following figure, where the view volume boundaries are established by the window limits x, w min, x, w max, y, w min, y, w max, and the positions z front and z back of the front and back planes. Viewport boundaries are set with the coordinate values x v min, x v max, y v min, y v max, z v min, and z v max. The additive translation factors kx, ky, and kz in the transformations are as shown in the equations below. Viewport clipping. Lines and polygon surfaces in a scene can be clipped against the viewport boundaries with procedures similar to those used for 2 dimensions, except that objects are now processed against clipping planes instead of clipping edges. Curved surfaces are processed using the defining equations for the surface boundary and locating the intersection lines with the parallelepiped planes. The 2-dimensional concept of region codes can be extended to 3 dimensions by considering the positions in front and in back of the 3-dimensional viewport, as well as positions that are left, right, below, or above the volume. For 2-dimensional clipping, we used a 4-digit binary region code to identify the position of a line endpoint relative to the viewport boundaries. For 3-dimensional points, we need to expand the region code to 6 bits. Each point in the description of a scene is then assigned a 6-bit region code that identifies the relative position of the point with respect to the viewport. For a line endpoint at position x, y, z, we assign the bit positions in the region code from right to left as shown here. For example, a region code of 101,000 identifies a point as above and behind the viewport, and the region code 000,000 indicates a point within the volume. A line segment can immediately be identified as completely within the viewport if both endpoints have a region code of 000,000. If either endpoint of a line segment does not have a region code of 000,000, we perform the logical AND operation on the two endpoint codes. The result of this AND operation will be non-zero for any line segment that has both endpoints in one of the 6 outside regions. For example, a non-zero value will be generated if both the endpoints are behind the viewport or both endpoints are above the viewport. If we cannot identify a line segment as completely inside or completely outside the volume, we test for intersections with the bounding planes of the volume. As in two-dimensional line clipping, we use the calculated intersection of a line with the viewport plane to determine how much of the line can be thrown away. The remaining part of the line is checked against the other planes, and we continue until either the line is totally discarded or a section is found inside the volume. Equations for three-dimensional line segments are conveniently expressed in parametric form. The two-dimensional parametric clipping methods of Cyrus-Beck or Liang-Bursky can be extended to three-dimensional scenes. For a line segment with endpoints P1 equals x1, y1, z1 and P2 equals x2, y2, z2, we can write the parametric line equations as x equals x1 plus x2 minus x1 into u, where u lies between 0 and 1. Y equals y1 plus y2 minus y1 into u. Z equals z1 plus z2 minus z1 into u. Coordinates x, y and z represent any point on the line between the two endpoints. At u equals 0, we have the point P1, and u equals 1 puts us at P2. To find the intersection of a line with the plane of the viewport, we substitute the coordinate value for that plane in the appropriate parametric expression and solve for view. For instance, suppose we are testing a line against the ZV min plane of the viewport. Then u equals ZV min minus Z1 over Z2 minus Z1. When the calculated value for u is not in the range from 0 to 1, the line segment does not intersect the plane under consideration at any point between endpoints P1 and P2. If the calculated value for u is in the interval from 0 to 1, we calculate the intersections x of xi and y of yi coordinates as xi equals x1 plus x2 minus x1 into zv min minus z1 over z2 minus z1. Yi equals y1 plus y2 minus y1 into zv min minus z1 over z2 minus z1. If either xi or yi is not in the range of the boundaries of the viewport, then this line intersects the front plane beyond the boundaries of the volume. This figure shows a side view of two line segments that are to be clipped against the ZV min plane of the viewport. For line A, a value of u that is outside the range from 0 to 1. For line B, intersection coordinates that are outside the range from yv min to yv max. Clipping in homogeneous coordinates. Pigs and other packages actually represent coordinate positions in homogeneous coordinates. This allows the various transformations to be represented as 4x4 matrices, which can be concatenated for efficiency. After all viewing and other transformations are complete, the homogeneous coordinate positions are converted back to three-dimensional points. As each coordinate position enters the transformation pipeline, it is converted to a homogeneous coordinate representation. X, y, z implies x, y, z and 1. The various transformations are applied and we obtain the final homogeneous point as shown in the matrix below. Where the homogeneous parameter h may not be 1, in fact h can have any real value. Clipping is then performed in homogeneous coordinates, and clipped homogeneous positions are converted to non-homogeneous coordinates in three-dimensional normalized projection coordinates. X dash equals xh over h, y dash equals yh over h, and z dash equals zh over h. We will of course have a problem if the magnitude of parameter h is very small or has the value 0, but normally this will not occur if the transformations are carried out properly. At the final stage in the transformation pipeline, the normalized point is transformed to a three-dimensional device coordinate point. The xy position is plotted on the device and the z component is used for depth information processing. Setting up clipping procedures in homogeneous coordinates allows hardware viewing implementations to use a single procedure for both parallel and perspective projection transformations. Objects viewed with a parallel projection could be correctly clipped in three-dimensional normalized coordinates, provided the value h equals 1 has not been altered by other operations. But perspective projections in general produce a homogeneous parameter that no longer has the value 1. Converting the sheared frustum to a rectangular parallelopiped can change the value of the homogeneous parameter. So we must clip in homogeneous coordinates to be sure that the clipping is carried out correctly. Also, rational spline representations are set up in homogeneous coordinates with arbitrary values for the homogeneous parameter, including h less than 1. Negative values for the homogeneous can also be generated in perspective projection when coordinate positions are behind the projection reference point. This can occur in applications where we might want to move inside of a building or other object to view its interior. To determine homogeneous viewport clipping boundaries, we note that any homogeneous coordinate position xh, yh, zh, and h is inside the viewport if it satisfies the inequalities xh over h lies between xv min and xv max, yh over h lies between yv min and yv max, and zh over h lies between zv min and zv max. Thus the homogeneous clipping limits are as shown below. Solved examples. Problem: find the intersection point of a plane and a line segment. Solution: suppose that the plane passes through the point r0, x0, y0, z0, and has a normal vector n equals n1i plus n2j plus n3k. Let the points p1, x1, y1, z1 and p2, x2, y2, z2 determine a line segment. The equation of the plane is n1 into x minus x0 plus n2 into y minus y0 plus n3 into z minus z0 equals 0, and the parametric equation of the line is x equals x1 plus x2 minus x1 into t, y equals y1 plus y2 minus y1 into t, and z equals z1 plus z2 minus z1 into t. Substituting this equation in the equation of the plane, we obtain n1 x1 plus x2 minus x1 into t minus x0 plus n2 y1 plus y2 minus y1 into t minus y0 plus n3 into z1 plus z2 minus z1 into t minus z0 equals 0. Solving this for t yields a parameter value ti at the time of intersection. Ti is shown here. We can rewrite this using vector notation as Ti equals minus n and r0 p1 bar over n and p1 p2 bar. The intersection points I, xi, yi, zi can be found from the parametric equations of the line as shown. If Ti lies between 0 and 1, the intersection point I is on the line segment from p1 to p2. If not, the intersection point is on the extended line. Parallel and perspective projections. Projection. Once world coordinate descriptions of the objects in a scene are converted to viewing coordinates, we can project the three-dimensional objects onto the two-dimensional view plane. There are two basic projection methods: parallel projection, perspective projection. Parallel projection. Coordinate positions are transformed to the view plane along parallel lines. An example of this is shown in the figure. Perspective projection is shown in the figure. Object positions are transformed to the view plane along lines that converge to a point called the projection reference point or center of projection. The projected view of an object is determined calculating the intersection of the projection lines with the view plane. A parallel projection preserves relative proportions of objects, and this is the method used in drafting to produce scale drawings of three-dimensional objects. Accurate views of the various sides of an object are obtained with the parallel projection, but this does not give us a realistic representation of the appearance of the three-dimensional object. A perspective projection, on the other hand, produces realistic views but does not preserve relative proportions. Projections of distant objects are smaller than the projections of objects of the same size that are closer to the projection plane, as shown in the figure. Parallel projections. We can specify a parallel projection with a projection vector that defines the direction for the projection lines. When the projection is perpendicular to the view plane, we have an orthographic parallel projection. Otherwise, we have an oblique parallel projection. This figure illustrates the two types of parallel projections: orthographic projection and oblique projection. Some graphics packages, such as GL on Silicon Graphics workstations, do not provide for oblique projections. In this package, for example, a parallel projection is specified by simply giving the boundary edges of a rectangular parallelopipe. Orthographic projections are most often used to produce the front, side and top views of an object as shown in this figure. Front, side and rear orthographic projections of an object are called elevations, and a top orthographic projection is called a plan view. Engineering and architectural drawings commonly employ these orthographic projections because lengths and angles are accurately depicted and can be measured from the drawings. We can also form orthographic projections that display more than one face of an object. Such views are called axonometric orthographic projections. The most commonly used axonometric projection is the isometric projection. We generate an isometric projection by aligning the projection plane so that it intersects each coordinate axis in which the object is defined, called the principal axis, at the same distance from the origin. This figure shows an isometric projection for a cube. The isometric projection is obtained by aligning the projection vector with the cube diagonal. There are 8 positions, one in each octant, for obtaining an isometric view. All 3 principal axes are foreshortened equally in an isometric projection so that relative proportions are maintained. This is not the case in a general axonometric projection, where scaling factors may be different for 3 principal directions. Transformations equations for an orthographic parallel projection are straightforward. If the view plane is placed at position ZVP along the ZV axis, as per this figure, then any point x, y, z in viewing coordinates is transformed to projection coordinates as xp equals x and yp equals y, where the original z coordinate value is preserved for the depth of information needed in depth queuing and visible surface determination procedures. An oblique projection is obtained by projecting points along parallel lines that are not perpendicular to the projection plane. In some application packages, an oblique projection vector is specified with 2 angles, alpha and phi, as shown in this figure. Oblique projection of coordinate position x, y, z to position xp, yp on the view plane. Point x, y, z is projected to position xp, yp on the view plane. Orthographic projection coordinates are on the plane x, y. The oblique projection line from x, y, z to xp, yp makes an angle alpha with the line on the projection plane that joins xp, yp and x, y. This line of length L is at an angle phi with the horizontal direction in the projection plane. We can express the projection coordinates in terms of x, y, L and phi as xp equals x plus L cos phi, yp equals y plus L sin phi. Length L depends on the angle alpha and the z coordinate of the point to be projected. Tan alpha equals z over L. Thus, L equals z over tan alpha equals ZL1, where L1 is the inverse of tan alpha, which is also the value of L when z equals 1. We can then write the oblique projection equations as xp equals x plus z into L1 cos phi, yp equals y plus z into L1 sin phi. The transformation matrix for producing any parallel projection onto the xy plane can be written as follows. An orthographic projection is obtained when L1 equals 0, which occurs at a projection angle alpha of 90 degrees. Oblique projections are generated with non-zero values for L1. Projection matrix has a structure similar to that of z-axis shear matrix. In fact, the effect of the projection matrix is to shear planes of constant z and project them onto the view plane. The x and y coordinate values within each plane of constant z are shifted by an amount proportional to the z value of the plane, so that angles, distances, and parallel lines in the plane are projected accurately. This effect is shown in this figure, where the back plane of the box is sheared and overlapped with the front plane in the projection to the viewing surface. An edge of the box connecting the front and back planes is projected into a line of length L1 that makes an angle phi with the horizontal line in the projection plane. Common choices for angle phi are 30 degrees and 45 degrees, which display a combination view of the front, side, and top, or front, side, and bottom of an object. Two commonly used values for alpha are those for which tan alpha equals 1 and tan alpha equals 2. For the first case, alpha equals 45 degrees, the views obtained are called Cavalier projections. All lines perpendicular to the projection plane are projected with no change in length. Examples of Cavalier projections for a cube are given in this figure. When the projection angle alpha is chosen so that tan alpha equals 2, the resulting view is called cabinet projection. For this angle, approximately equal to 63.4 degrees, lines perpendicular to the viewing surface are projected at 1/2 their length. Cabinet projections appear more realistic than Cavalier projections because of this reduction in the length of perpendiculars. This figure shows examples of cabinet projection for a cube. Perspective projections. To obtain a perspective projection of a three-dimensional object, we transform points along projection lines that meet at the projection reference point. Suppose we set the projection reference point PRP at position ZPRP along the ZV axis, and we place the view plane at ZVP as shown in this figure. We can write equations describing coordinate positions along the perspective projection line in parametric form as x dash equals x minus xu, y dash equals y minus yu, z dash equals z minus brackets z minus zprp into u. Parameter u takes values from 0 to 1 and coordinate position x dash, y dash, z dash represents any point along the projection line. When u equals 0, we are at position p equals x, y, z. At the other end of the line, u equals 1, and we have the projection reference point coordinates 0, 0, z, p, r, p. On the view plane, z dash equals z, v, p, and we can solve the z dash equation for parameter u at this position along the projection line. U equals z, v, p minus z over z, p, r, p minus z. Substituting this value of u into the equations for x dash and y dash, we obtain the perspective transformation equations as shown, where dp equals zprp minus zvp is the distance of the view plane from the projection reference point. Using a three-dimensional homogeneous coordinate representation, we can write the perspective projection transformation in matrix form as shown below. In this representation, the homogeneous factor is h equals zprp minus z over dp, and the projection coordinates on the view plane are calculated from the homogeneous coordinates as xp equals xh over h, yp equals yh over h, where the original z coordinate value would be retained in projection coordinates for visible surface and other depth processing. In general, the projection reference point does not have to be along the ZV axis. We can select any coordinate position XPRP, YPRP, ZPRP on either side of the view plane for the projection reference point. There are a number of special cases for the perspective transformation equations. If the view plane is taken to be the UV plane, then ZVP equals 0 and the projection coordinates are as shown below. And in some graphics packages, the projection reference point is always taken to be at the viewing coordinate origin. In this case, ZPRP equals 0 and the projection coordinates on the viewing plane are as shown below. When a three-dimensional object is projected onto a view plane using perspective transformation equations, any set of parallel lines in the object that are not parallel to the plane are projected into converging lines. Parallel lines that are parallel to the view plane will be projected as parallel lines. The point at which a set of projected parallel lines appears to converge is called a vanishing point. Each such set of projected parallel lines will have a separate vanishing point, and in general, a scene can have any number of vanishing points depending on how many sets of parallel lines there are in the scene. The vanishing point for any set of lines that are parallel to one of the principal axes of an object is referred to as a principal vanishing point. We control the number of principal vanishing points, 1, 2, or 3, with the orientation of the projection plane, and perspective projections are accordingly classified as 1-point, 2-point, or 3-point projections. The number of principal vanishing points in a projection is determined by the number of principal axes intersecting the view plane. This figure illustrates the appearance of 1-point and 2-point perspective projections for a cube. In this figure, the view plane is aligned parallel to the XY object plane so that only the object Z-axis is intersected. This figure shows the perspective views and principal vanishing points of a cube for various orientations of the view plane relative to the principal axes of the object. This orientation produces a 1-point perspective projection with a Z-axis vanishing point. For the view shown in part C of this figure, the projection plane intersects both the X and Z axes, but not the Y axis. The resulting 2-point perspective projection contains both X-axis and Z-axis vanishing points. Solved examples. Problem: show how region codes would be assigned to the endpoints of a line segment for the three-dimensional Cohen-Sutherland clipping algorithm for the canonical parallel view volume and the canonical perspective view volume. Solution: for 3D, the planes describing the view volume divide the three-dimensional space into 6 overlapping exterior regions, that is, above, below, to right of, to left of, behind and in front of view volume, plus the interior of the view volume. Thus, 6-bit codes are used. Let P, X, Y, Z be the coordinate of an endpoint. For the canonical parallel view volume, each bit is set to true 1 or false 0 according to the scheme as follows. Recall that sin A equals 1 if A is positive, 0 otherwise. For the canonical perspective view volume, the scheme is as follows. The category of a line segment is visible if both region codes are 00000, not visible if the bitwise logical AND of the region codes is not 00000, and clipping candidate if the bitwise logical AND of the region code is 00000. Problem: the unit cube which is shown in below figure is projected onto the XY plane. Note the position of the X, Y, and Z axes. Draw the projected image using the standard perspective transformation with A, D equals 1 and B, D equals 10, where D is distance from the view plane. Solution: we represent the unit cube in terms of the homogeneous coordinates of its vertices, as shown below. The standard perspective matrix is shown here. A with D equals 1, the projected coordinates are found by applying the matrix per K to the matrix of coordinates V, as given here. If these homogeneous coordinates are changed to three-dimensional coordinates, the projected image has coordinates as shown below. We draw the projected image by preserving the edge connections of the original object. Note the vanishing point at 0, 0, 0. With d equals 10, the perspective matrix is as shown below. Then, V and per K matrix results as shown. This is the matrix image coordinates in homogeneous forms. The projected image coordinates are then as shown below. Note the different perspectives of the face E', F', G', H' in the following figures. To a viewer standing at the center of projection 0, 0, minus d, this face is the back face of the unit cube. Problem: find the transformation for Cavalier projections with theta equals 45 degrees, cabinet projections with theta equals 30 degrees. Draw the projection of the unit cube for each transformation. Solution: a Cavalier projection is an oblique projection where there is no foreshortening of lines perpendicular to the xy plane. Let us take f equals 1 with theta equals 45 degrees. We have the matrix below. A cabinet projection is an oblique projection with f equals 1 by 2 with theta equals 30 degrees. We have. To construct the projections, we represent the vertices of the unit cube by a matrix whose columns are homogeneous coordinates of the vertices. To draw the Cavalier projection, we find the image coordinates by applying the transformation matrix par V1 to the coordinate matrix V. The image coordinates are then. Refer this figure. To draw the cabinet projection, refer this matrix. The image coordinates are then as shown here. This is the resulting figure. View volumes and projection transformations. View volumes and general projection transformations. In the camera analogy, the type of lens used on the camera is one factor that determines how much of the scene is caught on film. A wide-angle lens takes in more of the scene than a regular lens. In three-dimensional viewing, a rectangular view window or projection window in the view plane is used to the same effect. Edges of the view window are parallel to the XV, YV axes, and the window boundary positions are specified in viewing coordinates as shown in this figure. The view window can be placed anywhere on the view plane. Given the specification of the view window, we can set up a view volume using the window boundaries. Only those objects within the view volume will appear in the generated display on an output device. All others are clipped from the display. The size of the view volume depends on the size of the window, while the shape of the view volume depends on the type of projection to be used to generate the display. In any case, four sides of the volume are planes that pass through the edges of the window. For a parallel projection, these four sides of the view volume form an infinite parallel pipe as in this figure. For a perspective projection, the view volume is a pyramid with apex at the projection reference point, as shown in this figure. Examples of perspective projection view volume for various positions of the projection reference point are shown above. A finite view volume is obtained by limiting the extent of the volume in the ZV direction. This is done by specifying positions for one or two additional boundary planes. These ZV boundary planes are referred to as the front plane and back plane, or the near plane and the far plane of the viewing volume. The front and back planes are parallel to the view plane at specified positions Z front and Z back. Both planes must be on the same side of the projection reference point, and the back plane must be farther from the projection point than the front plane. Including the front and back planes produces a view volume bounded by 6 planes as shown in this figure. With an orthographic parallel projection, the 6 planes form a rectangular parallelopipe, while an oblique parallel projection produces an oblique parallelopiped view volume. With a perspective projection, the front and back clipping planes truncate the infinite pyramidal view volume to form a frustum. Front and back clipping planes allow us to eliminate parts of the scene from the viewing operations based on depth. We can then pick out parts of a scene that we would like to view and exclude objects that are in front of or behind the part that we want to look at. Also, in a perspective projection, we can use a front clipping plane to take out large objects close to the view plane that can project to unrecognizable sections within the view window. Similarly, the back clipping plane can be used to cut out objects far from the projection reference point that can project to small blots on the output device. Relative placement of the view plane and the front and back clipping planes depends on the type of view we want to generate and the limitations of a particular graphics package. With FIGS, the view plane can be positioned anywhere along the ZV axis except that it cannot contain the projection reference point. And the front and back planes can be in any position relative to the view plane as long as a projection reference point is not between the front and back planes. This figure illustrates possible arrangements for the front and back planes in relation to the view plane. The default view volume in FIGS is formed as a unit cube using a parallel projection with Z front equals 1, Z back equals 0, the view plane coincident with the back plane, and the projection reference point at position 0.5, 0.5, 1.0 on the front plane. Orthographic parallel projections are not affected by view plane positioning because the projection lines are perpendicular to the view plane regardless of its location. Oblique projections may be affected by view plane positioning depending on how the projection direction is to be specified. In FIGS, the oblique projection direction is parallel to the line from the projection reference point to the center of the window. Therefore, moving the position of the view plane without moving the projection reference point changes the skewness of the sides of the view volume as shown in this figure. Often, the view plane is positioned at the view reference point or on the front clipping plane when generating a parallel projection. Perspective effects depend on the positioning of the projection reference point relative to the view plane as shown in this figure. If we place the projection reference point close to the view plane, perspective effects are emphasized. That is, closer objects will appear much larger than more distant objects of the same size. Similarly, as we move the projection reference point farther from the view plane, the difference in the size of near and far objects decreases. In the limit, as we move the projection reference point infinitely far from the view plane, a perspective projection approaches a parallel projection. The projected size of an object in a perspective view is also affected by the relative position of the object and the view plane, as shown in this figure. If the view plane is in front of the object, nearer the projection reference point, the projected size is smaller. Conversely, object size is increased when we project onto a view plane in back of the object. View plane positioning for a perspective projection also depends on whether we want to generate a static view or an animation sequence. For a static view of a scene, the view plane is usually placed at the viewing coordinate origin, which is at some convenient point in the scene. Then it is easy to adjust the size of the window to include all parts of the scene that we want to view. The projection reference point is positioned to obtain the amount of perspective desired. In an animation sequence, we can place a projection reference point at the viewing coordinate origin and put the view plane in front of the scene, as shown in this figure. This placement simulates a camera reference frame. We set the field of view, lens angle, by adjusting the size of the window relative to the distance of the view plane from the projection reference point. We move through the scene by moving the viewing reference frame, and the projection reference point will move with the view reference point. General parallel projection transformations. In FIGS, the direction of a parallel projection is specified with a projection vector from the projection reference point to the center of the view window. This figure shows the general shape of a finite view volume for a given projection vector and projection window in the view plane. We obtained the oblique projection transformation with the shear operation that converts the view volume in previous figure to the regular parallelepiped shown in this figure. The elements of the shearing transformation needed to generate the view volume shown in figure are obtained by considering the shear transformation of the projection vector. If the projection vector is specified in world coordinates, it must first be transformed to viewing coordinates using the rotation matrix. The projection vector is unaffected by the translation since it is simply a direction with no fixed position. For graphics packages that allow specification of the projection vector in viewing coordinates, we apply the shear directly to the input elements of the projection vector. Suppose the elements of the projection vector in viewing coordinates are VP equals Px, Py and Pz. We need to determine the elements of a shear matrix that will align the projection vector Vp with the view plane normal vector n. This transformation can be expressed as Vp dash equals M parallel and Vp, where M parallel is equivalent to the parallel projection and represents a z-axis shear of the form as shown below. The explicit transformation equations in terms of shear parameters A and B are 0 equals Px plus Apz, 0 equals Py plus Bpz, so that the values for the shear parameters are A equals minus Px over Pz and B equals minus Py over Pz. Thus we have the general parallel projection matrix in terms of the elements of the projection vector as shown below. This matrix is then concatenated with transformation R and T to produce a transformation from world coordinates to parallel projection coordinates. For an orthographic parallel projection, Px equals Py equals 0 and M parallel is the identity matrix. From this figure, as shown below, we can relate the components of the projection vector to parameters L, alpha and phi. L cos phi over z equals minus Px over Pz, L sin phi over z equals minus Py over Pz. By similar triangles, we see that which illustrates the equivalence of the elements of transformation matrices. In equation z and Pz are of opposite signs, and for the positions illustrated in this figure, z is less than 0. General perspective projection transformations. With the fixed programming standard, the projection reference point can be located at any position in the viewing system, except on the view plane or between the front and back clipping planes. This figure shows the shape of a finite view volume for an arbitrary position of the projection reference point. General shape of the perspective view volume with the projection reference point that is not on the ZV axis. We can obtain the general perspective projection transformation with the following two operations. Shear the view volume so that the center line of the frustum is perpendicular to the view plane. Scale the view volume with the scaling factor that depends on 1 over z. The second step, scaling the view volume, is equivalent to the perspective transformation. A shear operation to align a general perspective view volume with the projection window is shown in this figure. This transformation has the effect of shifting all positions that lie along the frustum center line, including the window center, to a line perpendicular to the view plane. With the projection reference point at a general position xPRP, yPRP, zPRP, the transformation involves a combination z-axis shear and a translation, as shown below, where the sheared parameters are as shown in the equations below. Points within the view volume are transformed by this operation as x dash equals x plus a into z minus zPRP, y dash equals y plus b into z minus zPRP, z dash equals z. When the projection reference point is on the ZV axis, xPRP equals yPRP equals 0. Once we have converted a position x, y, z in the original view volume to position x dash, y dash, z dash in the sheared frustum, we then apply a scaling transformation to produce a regular parallel pipe. This transformation for the conversion is as shown in the equation below. And the homogeneous matrix representation is per the matrix shown. Therefore, the general perspective projection transformation can be expressed in matrix form as M perspective equals M scale and M shear. The complete transformation from world coordinates to perspective projection coordinates is obtained by right concatenating M perspective with the composite viewing transformation R and T. Viewing coordinates. Generating a view of an object in 3 dimensions is similar to photographing the object. We can walk around and take its picture from any angle at various distances and with varying camera orientations. Whatever appears in the viewfinder is projected onto the flat film surface. The type and size of the camera lens determines which parts of the scene appear in the final picture. These ideas are incorporated into the 3-dimensional graphics packages so that views of a scene can be generated given the spatial position, orientation and aperture size of the camera. Specifying the view plane. We choose a particular view for a scene by first establishing the viewing coordinate system, also called the view reference coordinate system, as shown in this figure. Figure shows a right-handed viewing coordinate system with axes xv, yv and zv relative to a world coordinate scene. A view plane or projection plane is then set up perpendicular to the viewing zv axis. We can think of the view plane as the film plane in a camera that has been positioned and oriented for a particular shot of the scene. World coordinate positions in the scene are transformed to viewing coordinates, then viewing coordinates are projected onto the view plane. To establish the viewing coordinate reference frame, we first pick a world coordinate position called the view reference point. This point is the origin of our viewing coordinate system. The view reference point is often chosen to be close to or on the surface of some object in a scene. But we could also choose a point that is at the center of an object or at the center of a group of objects or somewhere out in the front of the scene to be displayed. If we choose a point that is near to or on some object, we can think of this point as a position where we might want to aim a camera to take a picture of the object. Alternatively, if we choose a point that is at some distance from a scene, we could think of this as the camera position. Next, we select the positive direction for the viewing ZV axis and the orientation of the view plane by specifying the view plane normal vector n. We choose a world coordinate position, and this point establishes the direction for n relative either to the world origin or to the viewing coordinate origin. Graphics packages such as GKS and FIGS, for example, orient n relative to the world coordinate origin as shown in this figure. Orientations of the view plane for specified normal vector coordinates relative to the world origin. Position 1, 0, 0 orients the view plane as shown in figure A, while 1, 0, 1 gives the orientation in figure B. The view plane normal n is then the directed line segment from the world origin to the selected coordinate position. In other words, n is simply specified as a world coordinate vector. Some other packages, GL from Silicon Graphics for instance, establishes the direction for n using the selected coordinate position as a look-at point relative to the view reference point, viewing coordinate origin. This figure illustrates the method for defining the direction of n, which is from the look-at point to the view reference point. Another possibility is to set up a left-handed viewing system and take n and the positive ZV axis from the viewing origin to the look-at point. Only the direction of n is needed to establish the ZV direction. The magnitude is irrelevant because n will be normalized to a unit vector by the viewing calculations. Finally, we choose the up direction for the view by specifying a vector v called the view up vector. This vector is used to establish the positive direction for the yv axis. Vector v can also be defined as a world coordinate vector, or in some packages it is specified with a twist angle theta t about the zv axis as shown in this figure. This figure shows specifying the view up vector with a twist angle theta t. For a general orientation of the normal vector, it can be difficult or at least time-consuming to determine the direction for v that is precisely perpendicular to n. Therefore, viewing procedure typically adjusts the user-defined orientation of vector v as shown in this figure, so that v is projected into a plane that is perpendicular to the normal vector. Figure shows adjusting the input position of the view up vector v to a position perpendicular to the normal vector n. We can choose the view up vector v to be in any convenient direction as long as it is not parallel to n. As an example, consider an interactive specification of viewing reference coordinates using FIGS, where the view reference point is often set at the center of an object to be viewed. If we then want to view the object at the angle direction shown in the figure, we can simply choose v as a world vector 0, 1, 0, and this vector will be projected into the plane perpendicular to n to establish yw axis. Figure shows the choosing of v along the yw axis, setting up the orientation for the view plane in the desired direction. This is much easier than trying to input a vector that is exactly perpendicular to n. Using vectors n and v, the graphics package can compute a third vector u perpendicular to both n and v to define the direction for the x-v axis. Then the direction of v can be adjusted so that it is perpendicular to both n and u to establish the viewing yv direction. The viewing system is then often described as UVN system. See figure. Figure shows a right-handed viewing system defined with unit vectors u, v and n. Generally, graphics packages allow users to choose the position of the view plane with some restrictions along the ZV axis by specifying the view plane distance from the viewing origin. The view plane is always parallel to the XV, YV plane, and the projection of objects to the view plane correspond to the view of the scene that will be displayed on the output device. This figure gives examples of view plane positioning. Figure shows the view plane positioning along the ZV axis. If we set the view plane distance to the value 0, the XV, YV plane or UV plane of viewing coordinates becomes the view plane for the projection transformation. Occasionally, the term UV plane is used in reference to the viewing plane, no matter where it is positioned in relation to the XV, YV plane. But we will use the term UV plane only to mean the XV, YV plane, which is not necessarily the view plane. Left-handed viewing coordinates are sometimes used in graphics packages so that the viewing direction is in the positive ZV direction. But right-handed viewing systems are more common because they have the same orientation as the world reference frame. This allows graphics system to deal with only one coordinate orientation for both world and viewing references. We will follow the convention of fix and GL and use a right-handed viewing system for all algorithm development. To obtain a series of views of a scene, we can keep the view reference point fixed and change the direction of n as shown in this figure. Figure shows viewing a scene from different directions with a fixed view reference point. This corresponds to generating views as we move around the viewing coordinate origin. In interactive applications, the normal vector n is the viewing parameter that is most often changed. By changing only the direction of n, we can view a scene from any direction except along the line of v. To obtain either of the two possible views along the line of v, we would need to change the direction of v. If we want to simulate camera motion through a scene, we can keep n fixed and move the view reference point around, as shown in the figure. Transformations from world to viewing coordinates. Before object descriptions can be projected to the view plane, they must be transferred to viewing coordinates. Conversion of object descriptions from world to viewing coordinates is equivalent to transformation that superimposes the viewing reference frame onto the world frame using the basic geometric translate-rotate operations. This transformation sequence is: translate the view reference point to the origin of the world coordinate system, apply rotations to align the XV, YV and ZV axes with the world X, W, YW and ZW axis respectively. If the view reference point is specified to world position x0, y0, z0, this point is translated to the world origin with the matrix transformation as shown. The rotation sequence can require up to 3 coordinate axis rotations depending on the direction we choose for n. In general, if n is not aligned with any world coordinate axis, we can superimpose the viewing and world systems with the transformation sequence rz.ry.rx. That is, we first rotate the xw axis to bring zv into the xw-zw plane. Then we rotate around the world yw axis to align the zw and zv axes. The final rotation is about the zw axis to align the yw and yv axes. Further, if the view reference system is left-handed, a reflection of one of the viewing axes, for example the zv axis, is also necessary. The general sequence of translate-rotate transformations. The composite transformation matrix is then applied to world coordinate descriptions to transform to viewing coordinates. Another method for generating the rotation transformation matrix is to calculate unit UVN vectors and form the composite rotation matrix directly. Given vectors n and v, these unit vectors are calculated as shown below. This method also automatically adjusts the direction for v so that v is perpendicular to n. The composite rotation matrix for the viewing transformation is then the matrix R shown here, which transforms U onto the world XW axis, V onto the YW axis, and N onto the ZW axis. In addition, this matrix automatically performs the reflection necessary to transform a left-handed viewing system onto a right-handed world system. The complete world-to-viewing coordinate transformation matrix is obtained as a matrix product MWC, VC equals R and T. This transformation is then applied to coordinate descriptions of objects in the scene to transfer them to viewing reference frame. Viewing pipeline. The steps for computer generation of a view of three-dimensional scene are somewhat analogous to the processes involved in taking a photograph. To take a snapshot, we first need to position the camera at a particular point in space. Then we need to decide on the camera orientation as shown in this figure. Which way do we point the camera and how should we rotate it around the line of sight to set up direction for the picture? Finally, when we snap the shutter, the scene is cropped to the size of the window, aperture of the camera, and light from the visible surfaces is projected onto the camera film. We need to keep in mind, however, that the camera analogy can be carried only so far, since we have more flexibility and many more options for generating views of a scene with a graphics package than we do with a camera. This figure shows the general processing steps for modeling and converting a world coordinate description of a scene to device coordinates. This figure shows the general three-dimensional transformation pipeline from modeling coordinates to final device coordinates. Once the scene has been modeled, world coordinate positions are converted to viewing coordinates. The viewing coordinate system is used in graphics packages as a reference for specifying the observer viewing position and the position of the projection plane, which we can think of as an analogy with the camera film plane. Next, projection operations are performed to convert the viewing coordinate description of the scene to coordinate positions on the projection plane, which will then be mapped to the output device. Objects outside the specified viewing limits are clipped from further consideration, and the remaining objects are processed through visible surface identification and surface rendering procedures to produce a display within the device viewport. Conclusion. In this chapter, we have covered the following in detail: viewing pipeline, viewing coordinates, parallel and perspective projections, view volumes and projection transformations, clipping.